Welcome to the first presentation in Unit 9 entitled Here's to Chemistry, the Cause of and Solution to All Your Problems. It says, Everything is a miracle. It is a miracle that one does not dissolve in one's bath like a lump of sugar by Pablo Picasso. So the learning goals for this particular presentation are that students become familiar with key vocabulary regarding solutions, things like molarity, molality, that you be able to express concentration in molarity and molality, and that you be able to create a solution of known molarity. So here's what we already know. We know that we can express the number of molecules in moles, and we know that we generally do that because of the large number of molecules. Because the number of molecules is really, really large, we want to express it in moles where it reduces it down to a reasonable number. We don't want to talk about the fact that there are 10 times 10 to the 25th atoms in a particular beaker. Instead, we want to say something like there's 1 mole. It makes it a lot easier to work with. We also know that in order to physically react, molecules have to interact with one another. So in other words, if you have a molecule here and a molecule here, they're not able to interact because they're not in close enough proximity to one another. We also know that molecules can be classified as ionic, polar covalent, or nonpolar covalent based on the electronegativity difference between the bonds. So for example, if we have oxygen and oxygen, if those things are bonded, that is a nonpolar bond. If we have something like carbon and oxygen, that would be a polar bond because the oxygen wants those electrons more than the carbon does. And finally, if you have a metal and a nonmetal, something like sodium and chlorine, electrons are actually transferred, making them positive and negative ions. Okay, what we learned in the lab. We learned that solvents dissolve a solute to make a solution. I know that's kind of difficult to say, but the solvent is the material that does the dissolving. The solute is whatever you're dissolving. So if you look at Kool-Aid, the solvent would be something like water. If you were to look at the solute would be the Kool-Aid powder or sugar. And then the solution would be the combination of the sugar and the water together. Now, different solvents dissolve different solutes. So if you were to mix something like oil and water, they wouldn't dissolve. So you have to be real careful about what you're trying to dissolve. And then one measure of concentration is molarity, and molarity stands for moles per liter. So a solution is a combination of two different substances. Whenever you have a solution, that means that it's a homogeneous mixture. Now remember, homogeneous means that if you were to take a sample of it anywhere in the beaker or anywhere in the test tube, it would be the same in this bottom right corner as it would be in the top right, middle, bottom left corner. It's going to be the same everywhere. Now, a homogeneous solution means that although it is the molecules are interacting with the solution, it can still be physically separated. So a good example of that is if you had salt that was dissolved in water. Okay, if you have salt that's dissolved in water and you were to boil the water, all the salt would be left behind. Okay, examples of this are Dr. Pepper, Kool-Aid, salt water, and air. Now, a solute is the substance that is dissolved into another. So it's generally the smaller of the two. So an example of that is when you have sugar and you take sugar and you dissolve it in your tea. There is more water than there is tea. So because of that, you would say that the solute would be the sugar. Now, a solute can be a solid, a liquid, or a gas. And generally when it's dissolved, it becomes aqueous. Now, that's not always, it's not true for a gas, but generally we say when a solid is dissolved that it becomes aqueous. In order for something to become a solute, it must be able to physically mix with a solvent. And generally what you see is if we have something like, once again, salt is NaCl. And what happens is the negative part of the water molecules goes to the positive part of the sodium, and they kind of arrange like this. And that puts the positive hydrogens by the negative chlorines. Remember, opposites attract. So when you have a solvent, the solvent is the substance that dissolves the solute. It's generally the larger of the two. So once again, when you see something like coffee, the solvent is the water, and the solute would be the coffee beans, the sugar, or something like that. Now generally we think of solvents, they can be liquids, like we have here with water, or they can be a gas, if you were talking about nitrogen as the primary component of the atmosphere. One of the biggest things that's important as far as solutions is concerned is that like dissolves like. If you have a polar solvent, such as water, it will dissolve a polar solute or an ionic solute. And the reason is because polar and ionic solutes both create positive and negative charges. Water has positive and negative charges. There's positives on the hydrogens and negatives on the oxygen. Because of those, those are like things. They both have charged particles. As a result, water will dissolve ionic and polar solvents. So examples of that is water, and then you have some acids. A nonpolar solvent will dissolve nonpolar solutes. So for example, if you were to look at something like methane, methane is a CH4, and there is no partial positive, there is no partial negative. So because of that, it's not like these two. It doesn't have a positive charge or a negative charge, and as a result, methane will not dissolve into water. So when you look at the solubility chart, we classified things earlier as soluble or insoluble. And that's true to some degree, but everything is soluble to a certain amount. Now, the reason why things are classified as being insoluble is because there's very, very small amounts that are able to be dissolved. When something is classified as soluble, it has very, very high amounts of solubility. There is no absolute in terms of none of this will dissolve in water. So water is often called the universal solvent. Why is this the case, and is it true? And the answer is no, it's not true, because it will not dissolve nonpolar substances. So for example, if you were trying to take water and you were trying to dissolve oil, oil is nonpolar and water is polar. So because of that, water will not dissolve oil. Okay, so it is generally called the universal solvent because it will dissolve both ionic and polar solvents or polar solutes. So because of that, it takes a lot. Water will dissolve most things, but it will not dissolve everything. So although it is a very good solvent, it is not a universal solvent. It says a nutritional label for a soft drink is shown. Label the solute and the solvent based on the label. So the first thing you want to do is you want to look at the main ingredient. The main ingredient, remember, is going to be the solute. So let's change the color real quick so we can actually see what that looks like. You see the number one ingredient there is carbonated water. So you can say two things. You can say the solvent is carbonated water, or what I would say is actually the solvent is water, because water is the main ingredient. Now, you do actually dissolve carbonation, which is CO2, into it. So I would actually say that one of the solutes is CO2. You could also say solutes are things like sugar, caramel color, whatever that is, phosphoric acid, natural flavors, and caffeine. Everything that is not the solvent is a solute that's dissolved into it. It says one brand of antifreeze consists of 51% water and 49% ethylene glycol. Name the solute and the solvent. The solvent is the one that's the majority, so because of that I would say this 51% represents the solvent, and this 49% represents the solute. Okay, concentration. Whenever you're talking about a solution, it's really important that you specify the concentration of the solute. The concentration is, you can think of it as like the density. If you were to look at these two beakers right here, these two beakers actually contain the same number of molecules. So 1, 2, or 1, 1, 2, 2, 3, 3, and so on and so on. But if you were to look at this particular solution, it is way more concentrated. In other words, the density of these solute particles per volume is much, much greater. Even though they have the same number, this one has the same number in a smaller space. So because of that, the concentration is really, really high here, and the concentration is really, really low here. This we would call a concentrated solution. This we would call a diluted solution. Now, just because there's a large number of particles does not mean two particles can contact one another. So we said we were talking about the interaction of particles. It is much more likely that these two particles would interact than these two particles would interact, just because of the sheer proximity of the particles. So now one of the ways that we express concentration is in molarity. Molarity is a ratio of moles of the solute to volume of the solution. Now that is the total volume. Okay, it includes actually after you have dissolved the solute in the solvent. So if you're going to make a solution, well, we'll get to that a little bit later, but if you're going to make a solution, you have to account for the fact that the solute does have some volume. So now, we have molarity. Molarity is the expression of concentration. It's in molarity, capital M, or moles per liter, and it's a calculated substance, or it's a calculated quantity. We have moles of a solute, which is generally represented by an N. That's also calculated, and then we have the volume, which is the space, the amount of space the solution takes up, and it is measured in liters. You have molality. Molality is the ratio of moles to mass to measure concentration. So it's very, very similar to molarity, but the only difference is whether it's in the liters of the solution or whether you're in the kilograms of the solution. It makes a lot more sense to talk about kilograms of solvent whenever you're talking about things that heat up and cool down. Now the reason for that is whenever you heat something up, the volume can change. Whenever you cool something down, the volume can change. So whenever you're heating and cooling things down, it makes a lot of sense to talk about the molality of a solution as opposed to the molarity. But other than that, they're the exact same. Molality is a lowercase m. It's still moles of solute on the top, but on the bottom it's going to be kilograms of solvent instead of liters of solvent. So in this one it says, a student dissolves 1.3 moles of calcium hydroxide in 2.5 liters of solution. What is the molarity of the solution? So in this case, I'm looking for the molarity of the solution. I know the number of moles is 1.3, and I know the volume is 2.5. The equation that I have is the molarity is equal to the number of moles divided by the volume, or in this case we would say 1.3 divided by 2.5. At this point you would plug it in your calculator and you would say that 1.3 divided by 2.5 gives you a molarity of about 0.52 molarity, and then you want to specify what the solute is. So I would say CaOH2. This right here is the proper way to express the molarity of a substance. You have to say what the molarity is and then what the substance is that you're referring to the moles of. Okay, so the next example, it says a student dissolves 0.25 moles of sodium chloride in 325 mils of solution. What is the molarity of the solution? So we say, okay, the number of moles is equal to 0.25, and we're going to say that that's NaCl, moles. Okay, next we have the volume is 325 milliliters. And then finally it asks us to calculate the molarity. Now the first thing that you should recognize is, remember our formula is molarity equals number of moles divided by volume, but that volume is supposed to be in liters. So we need to convert milliliters to liters, and we do that by doing dimensional analysis. We say that there are 1,000 milliliters in 1 liter, or our total volume is 0.325 liters. Now that we have that, we can substitute our numbers in, and we would say 0.25 divided by 0.325 moles liters. And when we divide that out, we do 0.25 in our calculator divided by 0.325, and we end up getting something like 0.769231. Now, you should know that this right here is representing more accuracy than I should. Remember, you should use significant figures in your answer. And if you look, I have 2 significant figures here and 3 significant figures there, which means I need 2 in my answer. This should be 0.77 molarity NaCl. The next one says how many grams, so I'm looking for grams now, of copper 2 sulfate are in 250 mils of 0.25 molar copper sulfate. So the first thing that I need to do is I recognize, okay, I have the molarity of the solution this time. It's 0.25 molar CuSO4. I also have the volume is 250 mils, and just like in the previous example, I would need to convert this so that it is 0.25 liters. That allows me to solve for the number of moles. And I can say, okay, molarity is equal to N over V, or in our case, it's going to be 0.25 equals N over 0.25. So now what you need to do is you'd multiply both sides by 0.25. When you multiply both sides by 0.25, you end up getting 0.0625 is the number of moles. Now you have to be careful because this right here represents the moles of copper sulfate, but that is not what the question asked for. The question says how many grams of copper sulfate. So you have to remember, okay, grams to moles, and how do I do that? And you would do that using the periodic table. So 0.0625 moles of copper sulfate goes to 1 mole CuSO4, and then grams of CuSO4. Now, where you get this conversion factor from is the periodic table. So you would say copper is 63.5. You would say the sulfur is 32. And you would say oxygen is 16, but there are 4 of them. So whenever you multiply this out, you get 63.5 plus 64 plus 32, and you end up with 159.5. So now moles of copper sulfate is going to cancel out, and I'm going to be left with 159.5 times 0.0625. When you do that in your calculator, you get 9. We have to go to 2 significant figures at this point, so it would be 10 grams CuSO4. Whoops. Now, we need to talk about the idea of creating a solution. When you create a solution, you're trying to make something that you're going to use in the laboratory. So you need to use the molarity equation to determine the number of moles. So, okay, how many moles do I need to fit in this 100 milliliters? Molarity is equal to the number of moles divided by the volume. So you would actually do the math at this point. You'd say, okay, well, the volume is 0.1 because it's 100 mils, which is 0.1 liters. This is what I want to get. How many moles do I need? Just like we did in the previous example. So once you do that, you calculate the number of moles, you have to convert it to mass. So you calculate the mass required. Then the key to making a solution is that you actually add the mass first. And once you add the mass, now you fill the volumetric flask up until the meniscus gets to this line right here. This is the line on a volumetric flask, and the reason why that's important is if you were to fill this thing up to 100 and then add the powder has some volume, and that'll actually take your volume over 100 mils, and it would change your molarity. Now, some people think, well, it's not going to make that much of a difference, but if you're doing a lab in which you have to know the concentration exactly, like with something called a titration, okay, then it becomes really important that you know the exact value of the concentration of the solution. So here's an example. It says how many grams of ammonium phosphate are required to produce 2 liters of 2.5 molar solution. So once again, we say, okay, I've got volume is 2 liters. I know that I want to make a 2.5 molar solution. And then I know that I need to solve for the number of moles. So I'd say, okay, M equals N over V, or 2.5 equals N over 2. So the number of moles is going to be 5 moles, and specifically we're looking at ammonium phosphate. Now this question is kind of tough because you have to remember what ammonium phosphate is. You have ammonium and you have phosphate. This right here is a charge of -3. This is a charge of +1. So ammonium phosphate actually ends up being NH4 3PO4. Okay, now you would take this value right here and you would say, okay, I need to convert 5 moles of ammonium phosphate, and I would say 1 mole of ammonium phosphate to grams of ammonium phosphate. Remember, to go from grams to moles, you would use the periodic table. So you would look at this and you would say, okay, I have 3 nitrogens, I have 12 hydrogens, I have 1 phosphate, and I have 4 oxygens. So 4 oxygens, 4 times 16 is 64. 1 phosphorus, 1 times 31 is 31. 12 times 1 is 12. And 14 times 3 is going to be 42. Then you would take all these and add them up using your calculator, and you say 42 plus 12 plus 31 plus 64 gives you a value of 149. So you would take 5 moles, multiply it by 149, and you end up getting something like 745 grams. Now, technically this is not correct because of significant figures. You would look at this and say, wow, I only need 2 significant figures, and so this should really be 750 grams of ammonium phosphate. The final example says a student needs to make 500 mils of a 0.1 molar copper 2 solution. The only substance available to the student is copper 2 sulfate. Give specific directions on how the student can accomplish this task. Well, first, the student needs to do the math. Okay, and the math is involved. If we have the number of moles is what we're trying to solve for. Okay, we have the molarity is 0.1. We have the volume is, I'm going to go ahead and convert it. It's going to be 0.5 liters because remember, we've got to convert mils. So whenever you do this, you would say molarity is equal to the number of moles divided by the volume. You would take this and you would plug in 0.1 equals n times 0.5. The number of moles ends up being 0.05 moles. At this point, you would say, what do I have available to me? And some people get confused on this because they say, well, it's asking for this and I only have copper sulfate. Remember, copper sulfate will ionize in water. It will become Cu2 plus and SO4 2 minus. So whenever you do this, the concentration of copper is the same as the concentration of copper sulfate. So now it's a 0.05 moles of CuSO4, because that's what I actually have to add, divided by 1 mole, and then I've got to figure out the chemical formula again, or excuse me, the molar mass. So you say copper is 63.5, you have sulfur is 32, and you have oxygen, which there are 4 of, would be 64. Whenever you take those and add them up, 63.5 plus 32 plus 64 gives you 159.5 grams. Multiply that by 0.05 and you get about 7. So we have 3 significant, we only have 1 significant figure here, so that ends up being 8 grams. So we've done the math. We know that we need 8 grams of copper sulfate. So once we do that, we know we have 8 grams of copper sulfate. Here's what we would do. We would take and we would measure out 8 grams of copper sulfate. So we measure out 8 grams of copper sulfate. We would put it at the bottom of a flask, and then we would fill to a volumetric flask line the meniscus. So you want to fill it up to the volumetric flask line, the meniscus, to get the exact value.